Okay, so what we're going to do, we want to write a formula that says, need a formula that says at least k xi's are true. Okay, so what you do is, now this is actually going to use quite a lot of extra variables, but you're going to say y ij is true if true. You want to come up with these extra variables if at least j of x1 xi are true. Actually, I have to say, people usually don't go through this, because usually you get Cook's theorem and then people say, well, you don't have to do this. Clique reduces to sat because of Cook's theorem. But I think it's easier for you to understand Cook's theorem, why Cook's theorem is true, if you see that we can take clique and we can write the formula. Because after you've done this a couple of times, you get the feeling, you're like, yeah, Boolean formulas are pretty powerful. If I'm given a problem, then if I'm given a problem where I can recognize the solution in polynomial time, then I can probably write a formula that sort of says this has a solution. It's going to be polynomial size, and then it's an instance of sat. So, and that's sort of how Cook's theorem works. It says, okay, given any, you actually prove that given any problem where you can recognize, then you sort of take it and you turn it into machine language, and then you turn that into a sat formula. So I think it's easier if you go this way. How are you going to get this yi is true if at least j of x1 to xi are true? Well, that's going to be the case. You're going to say y11 if x1, actually in general, yi1, well, okay, y11 if x1, yi1 if either xi or yi minus 1, 1. So this is for I greater than 1. Right. So this feels a bit like dynamic programming, doesn't it? Right? So so this, if you can write if using a Boolean formula, right? It's just a double implication which says, like, if this, actually technically this is an if, so it's a bidirectional implication, and you're just saying, okay, it's not the case that one of these things is true and one of these things is false. Either they're both false or they're both true. And you can write that easily. You did learn that in second year. I assert that as true. I have to reset this. And I am not going to get through all of the stuff I wanted to get through today. Yeah, okay, so you say, okay, y11 is true if x1 is true. y1 if xi, or so if this is true, then I can get at least one thing true, or if I can get at least one thing true, and you say, okay, y I j if either y I minus 1, so j minus 1 and xi, or y, or y I minus 1j. Feels a lot like dynamic programming. Huh? Right. So you can write this and you say, okay, how many variables is it going to use? It's going to use like a quadratic number of variables, right? Because now I need one of these variables for sort of each cell in my matrix. And then eventually I'm going to say, okay, so I write this, and then in my clause I'm going to say all of these things are true, and then I'm also going to have ... and y y n k. So I can get, I'm appending this to my formula, and I'm saying that at least k of my n indicator variables are true. So this is not too hard. I mean, if you think about it, like, how would you write? You could write a formula that's saying, yeah, okay, this is it. So xi is true if you can put this thing in the clique, and then you just need to write this formula that says this. I wrote this up, I'm sure, last year. So it should be in the scribe notes. Okay, so that's this arrow. We can reduce clique to sat. So if somebody gives us a graph G and an integer k and asks us, is there a clique on size k? We don't know how to solve that in polynomial time, but we can turn it into a formula, a Boolean formula. In polynomial time, we can turn it into a formula such that the formula is satisfiable if and only if the graph has a clique of size k. So that means if somebody gave us a magic box, like this oracle thingy, and it would answer instances of sat and say yes or no correctly, then, and somebody wants to solve an instance of clique, then we can turn it into an instance of sat, and then we can use the magic box. So clique reduces to sat. And we saw that sat reduces to clique. So now, this is no longer in doubt. Clique reduces to sat. I don't think we are going to get time to fill in this arrow today, but it will go into the lecture notes. Okay, so let's see. We're not going to see. So basically, I'm going to draw in some of the other stuff. I hope you remember what it means for something to reduce to something else. So you also have, remember from when we drew this cool diagram at the beginning of the course, just checking that this is recording again, because yes, I'm super paranoid. We also had Hampa. We had three-colorability. We had planar three-colorability. We had four-colorability. Now remember, planar four-colorability, planar five-colorability, planar six-colorability, they are not hard because planar four-colorability is always just yes. If it's a planar graph, it's always four-colorable, or five-colorable, or six-colorable, whatever colorable. Except it's hard for three. So remember, two-colorability is easy for planar and non-planar. Three-colorability is hard for planar and non-planar. Four-colorability is hard for general graphs, but easy for planar graphs. So, obviously, if we can solve three-colorability, we can solve planar three-colorability, because you just ignore the fact that the graph is planar. Right? So if you have a magic box that tells you whether or not a graph can be three-colored, you just don't tell the magic box that it's a planar graph. Right? So clearly, this is true. And we saw in class, actually, let's move three-colorability over here. We saw at the beginning of the lecture, right, so if you wanted to reduce three-colorability to four-colorability, you just added another vertex and made it and attached it to everything. So now, if the original graph could be three-colored, then you can four-color this new graph. And if this new graph can be four-colored, then this new vertex has to be a different color than everything else, so you just take it off and the remainder is three-colored. So three-colorability reduces to four-colorability. Planar three-colorability reduces to three-colorability. What I'm probably, how much time do we have? Not a lot. So then, actually, all of this stuff, they turn into big cycles. You can reduce hand path to 3-sat. You can reduce, you can reduce hand path to sat. You can reduce sat to 3-sat. You can reduce 3-sat to hand path. Actually, you reduce 3-sat to directed hand path, and you reduce directed hand path to hand path. You can reduce four-colorability to sat. Now, what we're going to see next, I want to show you this one, because this is cute and easy. But the one we're going to do now is that 3-sat reduces to three-colorability. Okay? So if somebody gives you an instance of 3-sat, then you can turn it into a graph, G, such that G is, so somebody gives you a formula. Someone gives us a 3CNF formula, Boolean formula, F. We can build a graph G such that G is three-colorable if and only if F is satisfiable. And I hope that doesn't take us 15 minutes. Okay, so does anybody remember what this cute little formula was that I used for clique? If somebody could write that in the chat, that would be great. So, running out of board space here. But the idea is, what we're going to do is we start with a triangle. And we're going to call whatever color this vertex gets, we're going to call that color true. And we're going to call this one false. And we're going to call this one base. Okay? And then for base, for each literal in the formula F, so we're going to have x1 and not x1, and x2 and not x2. And there was, I'm going to write base over here so that I can have base, and I can have x3, not x3. x4, not x4. Okay? So does everybody see that if you want to three-color this, true has to get a color, false has to get a different color, base has to be a different color than all of those, and then both of these. And that means one of these have to both be different colors than each other and different colors than base. So one of them has to be the same color as true, and one of them has to be the same color as false. So that's sort of forcing us to color our literals. The literal is the positive, literals are positives and negatives of the variables. That's going to make us color these things correctly. Now, what we're going to have is for each clause, nobody wrote the formula in the chat. Does anybody remember what it was? Okay, I'm going to do it again. Well, so let's say that we had x1 or, what was it, not x2 or x3. So what we're going to do is write a little, now these are this, when I write x1, it's actually this x1. Okay, this vertex, I'm just writing it twice, but it's actually all connected. Okay, it just makes it hard to draw the stuff. But actually, imagine that these two circles are the same. And not x2 and x3. I really miss having physical classes. Like, I don't know, I look and it's like, I see nobody's writing, or people, oh. Okay, so what you do is you sort of make a graph that I'm trying to remember. Just a second, I think I have this written down. Oh, right, x1 or not x2 or x3. Okay, so I did remember it correctly. Just let me see what you do. Yes, okay, and then you do this, and you do this. Yeah, okay, this is easy. So, if this is you're just going to have to trust me that if one of these, if all of these are false, remember all of the literals have to be true or false. So if all of these are false, so let's say false is red, right? So if x1 is red, so if base is blue, 10 minutes. Then, so let's say true is green, false is red, base is blue. So now we're going to say x2 is also, not x2 is false. So if all of these are false, x3 is false. So if all of these are false, then one of these has to be true and one of these has to be base. Okay? It doesn't really matter which one is true and which one is base. Where is blue? Because it means this one has to be false. So if this is false and this is false, just a sec. Have I for yes? Oops. Sorry. Ah, too many pens. This has to have another of these. Okay, so if this is false and this is false, one of these has to be true and one of these has to be base. let's just reverse the order for fun. And that means this has to be false. Right? So if these are all false, this has to be false. I hope I copied it. It'll be in the, yeah, but I just needed the first one. And I'll check the formulas before I type up the course notes. Don't worry about it. As long as people sort of believe that if these three things are false, then the output has to be false. Now, let's suppose that one of these is true, right? So, I'm going to switch this, and I'm going to say x3 is true, not x3 is false. So that means x3 is true. This is now green. Don't know if you can see that this is green, but it is green. So now, this still has to be red. But now we have a red, we have a green, so we can put a red here. And we can put a blue here. So we can put a true here. So you can go through and check that if all of these are false, this is false. If 1, 2, or all 3 of these is true, then this can be true. Okay? So then I just have to look again because I didn't actually memorize. Yeah, okay, so this is easy. So then what we do is we take this and we connect it to the base, to this vertex. And we also connect it to false. So that's saying this has to be, for this graph to be 3 colorable, this has to be the same color as true. So therefore, it's saying this graph is 3 colorable if and only, and you do this for every clause. So remember, these 3 things, this x1 is this. So it's not like hanging off, it's not a separate graph. And this base is this. So now you get this graph that's 3 colorable if and only if your formula is satisfiable. So we have that 3sat reduces to 3 colorability. If there exists a polynomial time algorithm for 3 colorability, then there exists a polynomial time for 3sat, and so I'm going to put in dashed lines of all of the other things that I would like to show you today that we're not going to have time, but you can read about them on the internet. So I'm not going to, so 3 colorability, I'm not going to show that. What I am going to, Satan transform will be in the lecture notes. You can do this reduction. Like obviously if you can solve sat, you can solve 3sat. That's trivial, okay, because 3sat is a special case of sat. This is easy. To actually reduce sat to 3sat, you need this Satan transform, which I showed. Somehow I had time last year and the year before. So now what we're going to see in the remaining 4 minutes, yeah, maybe, is we're going to reduce 4 colorability to, we're going to get this stuff out of the way so I can draw the arrow. We're going to reduce 4 colorability to sat, which is again one of these things that people don't usually see because this arrow just follows from Cook's theorem. But since we haven't seen the proof of Cook's theorem, I want you to understand sort of how SAT is powerful enough that SAT can be NP complete. If you can do SAT, you can do any of these problems. So the answer is, so now somebody gives us a graph G, we can build a formula, a SAT formula, a Boolean formula F, such that G is actually, I don't have to reverse this order because it's an if, so the implication goes both ways. So F is satisfiable if and only if, but now I want G is 4 colorable. Okay? In fact, this would also work if it were 5 colorable, 6 colorable, whatever. Okay? So what do you do? Again, for each vertex you have a, well now for each vertex you have 4 indicator variables. Okay? So you have, for each vertex VI, we have, let's say, Ri, Bi, and Gi. Okay? So Ri says that Ri is true if and only if Vi is red. Bi is true if and only if Vi is blue. Gi is true if and only if Vi is green. Okay? So what we are going to have is Ri implies not Bi. I hope you know how to write implications as logical formulas. Ri also implies not Gi. Bi. So Bi implies not Ri, just in case. Bi implies not Gi. Gi implies not Ri. Gi implies not Bi. So it can't be 2 colors at once. God, I'm out of time. I can put this on the next assignment or something. Okay, just finishing. So what you're going to do is for each vertex, you write these formulas that say, okay, it's a color, it's not 2 colors, it's not 3 colors. Perhaps this would be 3 colorability. And you also need some, for 4 colorability, you have yellow. Okay, and you also have yellow in here. And so you say, okay, it's one of the 4 colors, each vertex is one of the 4 colors, and only one of the 4 colors. And then for each edge, Vi, Vj, you write Ri implies not Rj, Rj implies not Ri. Okay, so you just write out the little formulas that say, if you have an edge, it's not true that these 2 vertices are the same color. So now you get a big formula, but it's not too big, it's still only polynomial size, and it says this graph is 3 colorable. Okay, the formula is satisfiable if and only if the graph, 4 colorable. Graph is satisfiable, and you could do this for 5 colorable, 6 colorable, whatever, right? So 4 colorability reduces to SAT. Okay, so that sort of gives you an idea of why SAT is so powerful. So questions? That was all totally clear. Woo. I thought it was a bit fast, but if people thought that was the right speed, that's great. Is anybody still here? I'm down to 12 people. Yes, it was totally clear. Okay. Or yes, you have questions. Well, yes, I am here. Oh, okay. So I hope the lecture notes will be clearer. you can see why this stuff is kind of cool, right? I mean, you're going to see like all of these things, all of these paths, they all lead back to here. All roads lead to 3-sat. So you can see I managed to get to, I didn't get 3